All right, so with that little introduction, let's go on and look at some problems from this week's assignment. So here's one of the problems. You have a magnetic field, which depends on time. It points in the z direction, so it's k hat b0 plus beta 1t. You see it as a time dependence. But whenever there's a time-dependent magnetic field, you can expect electromagnetic induction to occur. In this magnetic field, you have a copper ring with some radius A and some resistance R. So I guess this would be A. And then the copper ring has resistance R. The problem is to calculate the current in the ring. And it's a combination of Faraday's law and Ohm's law. Faraday's law says that the changing flux produces EMF. Then Ohm's law says that the current is the EMF divided by the resistance. So we start with Faraday's law. The EMF is actually negative d phi dt, where phi is the magnetic flux. That means the flow of magnetic field through the surface bounded by the coil. So that's the integral b dot dA. Now, if this surface is in the xy plane, then dA points out of the xy plane in the same direction as the magnetic field. So this will just be b0 plus beta 1t times the area, pi a squared. And now you take the derivative, or actually the negative derivative, to get the EMF. This term doesn't contribute. It's this term, the time-dependent term, which gives an EMF, which is minus beta 1 times pi a squared. And then the current would just be that EMF divided by the resistance, which is given in the problem. So that's a good example of the use of Faraday's law. There's a changing magnetic field, there's a changing flux, and that generates an electromotive force by electromagnetic induction. And this will be circulating around the change in B. Now, will it be clockwise or counterclockwise? Well, the sign here will tell you if it's clockwise or counterclockwise. Here's another problem from the assignment. There's current in this wire. In this long straight wire, there's a current that depends on time. Now we know from last week, if there's a current, there's a magnetic field. And if the current depends on time, then the magnetic field depends on time. And the direction of the magnetic field curls around the current. So up here, the magnetic field points outward, out towards you, out of the screen. In other words, in the z direction. So there's a magnetic field in the z direction, and that makes flux through this little rectangular loop. Now the problem is to calculate the current in the rectangular loop. And it's just like the other problem. It's a combination of Faraday's law, which determines the magnetic field, and, well, no, Ampere's law really determines the magnetic field. Faraday's law determines the EMF, which is the derivative of the flux. So here's a result from last week. The magnetic field due to a wire, a straight wire. It's mu naught I over 2 pi r. Now what's r? Well, r is variable. This distance is r. So at a distance r, or I could just well call that y, from the wire, there's a magnetic field, mu naught I over 2 pi y. That's the result from last week. Magnetic field points out of the page by the right-hand rule. And so the flux will be the integral of bz times dA. Flux is field passing through an area. The field is B in the Z direction. The area is also in the Z direction because it's perpendicular to the surface. Surface is in the XY plane, so the field is in the Z direction. What's the area of this little section of the rectangle, which is at a distance y from the wire? Well, it's dy, where y goes from C to D, times the length here, which is B minus A. So here's the area, B minus A dy. So I have a constant mu naught I over 2 pi. I have another constant B minus A. Now I have the integral dy divided by y. And you'll remember from calculus, dy divided by y is the log of y. And you have to evaluate that at the upper end point, which is y equals d, minus the lower end point, which is y equals c. Or I could write this mu naught I over 2 pi. This current is the current in the wire along the x-axis. B minus A, that's the length of the rectangle, log of D minus log of C, or by high school algebra, remember that's the log of D divided by C. So that's the flux. And to do that calculation, you had to know the magnetic field produced by a current in a wire. The result from last week. And now the electromotive force around this rectangle is minus d phi dt. That's Faraday's law. So of a time-dependent magnetic field, time-dependent magnetic flux, that's going to imply electromotive force by Faraday's law. So we have these constants, mu naught I1 over 2 pi. Well, no, I1 is not constant. I1 is given by this time dependence. So in fact, that's where the time dependence is. So when I differentiate with respect to t, I'm really differentiating I1. I have these constants, mu naught over 2 pi, b minus a, log of, this is wrong, log of d divided by c. So that's the log of this constant. And then the derivative of I1, the I1 dt. Now that's the EMF around the rectangular loop. But what you're supposed to calculate is the current around the rectangular loop. And that comes again from Ohm's law. Current is the voltage divided by the resistance. The voltage is this electromotive force. The resistance, I guess, is probably, yeah, the resistance is given in the problem. So that will also depend on time. So you have to know at what time, but that's specified in the problem. You're supposed to calculate the current at the time 1.5 tau, where tau is a parameter here. Must be given in the problem someplace. Tau is 0.05 seconds. So you evaluate this derivative and then you plug in the number 1.5 times 0.05. So this is a typical problem involving Faraday's law. You use Faraday's law to determine the electromotive force, then you use Ohm's law to calculate the current, if that's part of the problem. All right. Here's another problem from the assignment. There are two coils of wire. C1 is a larger coil, C2 is a smaller coil, and the current I is delivered, let's say from a battery or something, to C1. So coming into a point on C1 and then going out from the same point but not in contact, there's a current I. That current is I1. And that is given, and it's time dependent. So again, it'll be just like the previous problem. There's a time dependent current, there must be a time-dependent magnetic field. And time-dependent magnetic field, by Faraday's law, gives an electromotive force. And the question is, what's the electromotive force around the little circuit? C2. So here's the current. Here's the current I1. It starts at 0, and then it increases to some final value I0, and kind of approaches I0 exponentially. Then the electromotive force around C2 will be the negative rate of change of the flux. So again, I have to calculate the flux, the integral B dot dA. Now this is the integral around that little disk enclosed by C2. And we're going to make an approximation. We're going to say, well, since this is such a small area, we'll just take the magnetic field in this little small area to be constant. It's not exactly constant. The magnetic field would vary with distance from the origin. But to a first approximation, I could just say, well, for such a small area, I can just take the value of the magnetic field throughout that circuit, throughout that little disk, to be constant. In other words, it's B at 0. Now, as for the direction, well, by the right-hand rule, if the current is, what's that, counterclockwise, then the magnetic field points outward, out towards you by the right-hand rule. That's in the Z direction. Here's X, Y, and outward is Z. Now, the area of this little disk is also in the Z direction. Because remember, the area of a surface points perpendicular to the surface. So dA is K hat times the area. Now, the area of that little disk is pi R2 squared. So I have BZ at 0, pi R2 squared. And it's an approximation, but it's a good approximation as long as R2 is small compared to R1. And, you know, in the problem, R1 is 0.8 meters, R2 is only 1 centimeter. So indeed, R2 is much less than R1. So this is a good approximation. Now you have to know this magnetic field on the circuit of, on the axis of a ring. And this is a problem that was done in the previous chapter. So suppose you have a ring of current, and that's in the XY plane. So perpendicular to that is the Z axis. Well, by the right-hand rule, if your fingers curl on around in the direction of the current, then your thumb points in the direction of the magnetic field. That'll be in the minus Z direction. Or if we look over here, this is a clockwise current. So the magnetic field is pointing away from you. That's in the negative Z direction. So the magnetic field points in the negative Z direction. And the formula for the magnetic field was derived in the previous chapter. This would be chapter 28, I guess it would be. It's mu naught I over 2 times R1 squared over Z squared plus R1 squared to the 3/2 power in the minus K hat direction. So in the negative K direction. So that's a result that you can find in chapter 28. It's equation 28.9. Now that would give you the magnetic field anywhere on the axis of the ring. We want to know at the origin. In other words, we want to know where Z is equal to 0. So if I said Z equals 0, what I have here is R1 cubed over R1 to the R1 squared to the 3/2 power, which is R1 cubed. So in other words, BZ at 0 is minus mu naught I over 2 R1. So the EMF is going to be the derivative of phi, and phi is proportional to I, so it'll be the derivative of I. The constants will be pi r2 squared mu 0 over 2 r1. There's a minus sign here, but there's also a minus sign here, so it'll come out to be a plus sign. And finally, the current in that little circle around the origin is the electromotive force divided by the resistance of that little circle. So that's, again, something given in the problem. Now, again, that will depend on the time. So you have to evaluate that current at a certain time. What time? Well, it says in the problem, what's the current at, again, 1.5 times the constant tau, which determines how fast the current is approaching the constant value. So all of those three problems were kind of similar. They all started out with some given information, a time-dependent magnetic field from which you calculate the flux and the derivative of the flux. And then to get a current, you have to divide the EMF, which is the derivative of the flux, well, apart from the sign, by the resistance. All right, so any questions about those three problems? Just unmute your microphone and speak up if you have a question to ask. Okay, then. Let's go on to this problem, which is a little more involved. This is a problem from the book. It's a problem at the end of the chapter 29. There's a section of the book on mutual inductance. And this is an example of mutual inductance. You have two coils of wire. You have coil C1, which is kind of short, and it surrounds the second coil C2, which is longer. And you're given the current in C1, and you're trying to calculate the potential difference from one end of C2 to the other, the induced potential difference across coil C2. We can think of C2 as a solenoid. It's a long helix of wire. We can think of C1 as kind of a shorter set of a few loops of wire carrying a current I1. All right. Now, I1 is given here. It's time dependent. And I1 creates a magnetic field, which by the right-hand rule points in this direction. So there's a magnetic field in this direction due to this coil of wire, due to current I1. And in fact, the flux of that magnetic field will be proportional to I1. I1 is just alpha times T. So we'll eventually take the derivative of I1. That's just the slope of I1 as a function of T. That's just alpha. Now, okay, so the problem is to calculate delta V2. Now, there's a similar problem in sections 6 and 7. I think it's actually in section 7 of the mutual inductance of a solenoid and a coil of wire. Well, that's what we have here, the mutual inductance of a solenoid and a coil of wire. So this is an example which shows that the mutual inductance of coil 1 due to the current in coil 2. That's called M21. So the current goes through 2 and creates flux through 1. And the calculation is N1 phi 2 to 1 over I2. So the current in coil 2 gives a flux through coil number 1. And the definition of mutual inductance is just the ratio between the flux and the current. Actually, in the case of coil 1, there are n turns of wire, so there'll be n times as much flux. So we can calculate M21 for this situation. It'd be N1, that's the number of turns in coil 1, divided by I2. Now the flux will be the magnetic field times the area. And you remember the magnetic field for a solenoid. It's mu naught times N over Li. That's the current in the solenoid. So that's I2. And the area of the solenoid is pi R2 squared. So the current cancels out. And we just get constants that depend on the parameters of the solenoid and the coil. It depends on N1, it depends on N2, depends on L2, depends on R2, the area of this solenoid. Now that gives us M21, or phi 2 goes to 1. But we want the opposite of that, because we want to know what's the potential around coil 2 due to the current in coil 1. So we want, well, of course, the potential around coil number 2 is the mutual inductance for 2 created by the current in 1 times di1 dt. What I have here is M for coil 1 due to coil 2. What I need is M for coil 2 due to current in coil 1. Now it's sort of hidden in the chapter, but if you read that chapter very carefully, you'll see that the authors point out that M12 and M21 are in fact equal. So I can use this result to determine the mutual inductance and apply that to this potential. So the potential across the solenoid C2 is minus M di1 dt. di1 dt is just alpha. You need to know this fact, that the mutual inductance of 1 due to the presence of current in 2 is the same as the mutual inductance of 2 due to a current in coil number 1. And you find that written just after this calculation in the book, but it's sort of hidden. Now, self-inductance is something you're likely to find on the exam and on the homework. That's self-inductance. Mutual inductance is a little more complicated. So you might not find mutual inductance on the exam. You might not find, well, I can't guarantee it, but self-inductance is more likely to appear in a homework problem or on an exam problem. Self-inductance and mutual inductance are described in these two sections. If you look at the end of chapter 29, on page 900, there is something called the exam study guide. It shows you what to study. Shows you what to study for an exam, according to these authors. And these are some of the items in the study guide. The definition of self-inductance is flux divided by current for one coil of wire. In other words, you want the flux through a coil of wire, which is produced by that very current. So that's called self-inductance. And that's the flux divided by the current times the number of turns of wire. Now, mutual inductance is different, but this is self-inductance. The self-inductance of a solenoid is written down in the exam study guide. So there's a calculation of self-inductance. It's mu naught n squared L over L times A, where n, little n, is the number of turns divided by the length of the solenoid. So that's self-inductance of a solenoid, and that's something which is included in the study guide. Then the self-induced potential difference across an inductor is minus L di dt. That just follows from Faraday's law. This is minus d phi dt, where phi is L times I. It's negative, so it's what's sometimes called back EMF. Well, those are all given in the exam study guide. They all concern self-inductance. What about mutual inductance? Well, that's not actually given in the exam study guide. So evidently that's a little more involved, but it's quite a bit related. I mean, self-inductance is the ratio of flux over current. Mutual inductance is also the ratio of flux over current, but it's the flux through one coil due to the current in the other coil. So that would be M1 into 2 due to current in coil number 1. And then there's also M2 goes to 1, which is flux over current, where the current here is the current in coil number 2. And then by Faraday's law, the EMF through one coil is d phi dt, so it's minus d phi dt, so it's minus m di1 dt, or through the other coil, it's minus m di2 dt. But then it can be shown, it's not really explained in the book, but it is stated, that these two different kinds of self-inductance are in fact equal. And that's what you needed to do this problem. One final problem from a homework assignment this week is what's called an RL circuit. A circuit where there's resistance and inductance and a direct current. Now, in the next chapter, we're going to consider alternating currents. And inductance is very important for alternating currents, as you'll see. But this is a little bit different kind of thing where there's a battery. Instead of an AC generator, there's a battery. So there's just a direct current. And that's called an RL circuit. It's got an electromotive source, which you should just think of as a battery, which can drive a current in this direction from the positive electrode to the negative electrode. So that would be, what would that be, clockwise. There's a resistor and an inductor in series. So the current, there's current through the resistor, there's current through the inductor. And the Kirchhoff loop rule says that if you calculate the change in potential as you go around the loop, there's the change in potential across the battery is equal to EMF minus the change in potential energy across the resistor, which is minus IR. Well, it's plus the change of potential, which is negative, and then plus the change of potential across the inductor, which is L di dt. Back EMF. So, since it's a back EMF, this is like the positive side, and this is like the negative side. So the change is from negative to positive. It's positive, L di dt. Now, this differential equation can be solved, and that's given in the book. It's V over R, 1 minus e to the minus t over tau, and tau is the time constant for an RL circuit, which is the inductance divided by the resistance. You probably remember when we talked about capacitors, we also considered RC circuits, where you had a resistor and a capacitor. And attached to a battery, the capacitor will get charged up. But here there's nothing to get charged up. It's just that the current starts at 0 when time is 0, and then gradually increases until it's just V naught over R. But the RC circuit and the RL circuit are related when you have direct currents. Now, in the next chapter, we'll have alternating currents. All right, so this is the solution for the current as a function of time. Now, the problem, you're supposed to calculate, well, okay, so part A says calculate the current as a function of time. That's given in the book. Now, that's not asked, you're not asked to solve that for the, answer that for ln kappa. You're supposed to answer about energy. So what's the energy supplied by the battery? What's the energy dissipated in the resistor? And what's the field energy stored up in the inductor? So you have to remember, power in a battery is current times voltage. The energy is the integrated power. So it's the integral, the current times the voltage. And you know the current from solving Kirchhoff's loop rule. So it's just a bit of an integral to do here. Now will give me the energy that has been supplied by the battery as the current is increasing to V over R. And part C is to calculate how much of that energy is dissipated in the resistor in the form of heat. And you have to remember, the power in a resistor is I squared R. That power is lost to the circuit. It's lost in the form of heat. The resistor gets hot. Now, you know what I is. Now, you want the integrated energy, or the integrated power is the energy. So that's this I squared, V squared over R, 1 minus e to the minus t over tau squared dt. So that will give you the amount of energy that was dissipated in the resistor and transferred to the surroundings in the form of heat. And finally, part D is to calculate the field energy stored in the inductor. And again, the energy in an inductor is 1/2 Li squared. There's nothing to integrate here. The integral when the current is I is 1/2 Li squared. Now, energy should be conserved. So the amount of energy supplied by the battery, U sub B, should be equal to the amount of energy that was transferred to the surroundings in the form of heat. That's U sub R, the joule heating of the resistor, plus the amount of energy that's been stored up in the inductor, which is U sub L. So you're going to get answers to B, C, and D, and they should combine in this way. All right, so those are the problems for the assignment, the last part of the assignment. I guess it's homework assignment number 7. We don't really have anything more to go over tonight. Are there any questions? Did I have my microphone on?
Yeah, you did.
Okay, good.
I have a question.
Yeah.
Do you have an email or anything that I could contact you for help or questions outside of this hour each week?
Yes. I'm not sure if email is the best way to collect information.
Okay.
If you have a question specific about the problem, you can write the question in the discussion page. And then hopefully somebody will answer it. Maybe me, maybe somebody else in the class will answer your question. But
Okay.
yeah, I mean, if you want to send me an email question, it's just stump@msu.edu. And I
Okay.
would say, if you put questions on the discussion board, you know, if you put a specific question, something you're not understanding on the discussion board, somebody will probably answer that. Now you have to be quick, careful. Don't put it on the last day before the homework is due, because somebody might not look at it that day. So you got to put it in a day or two early so somebody will see it and try to answer it. But yeah, if you want to send me a question, try stump@msu.edu.
Okay. Thank you.
Any other questions? Okay, well, you have until Thursday late night to do this homework, and then there'll be one more chapter before the second hour exam, before the second midterm exam. So try to get these done on, don't leave them till the last minute. Try to get them done in a timely fashion. And now let me stop sharing. Well, let me stop recording.